All right, time for our video on day 16 from Advent of Code 2022, and this was quite possibly the hardest problem of the whole sequence. I'm now on these series of videos that I'm doing completely after the fact, after having done all 25 days, and I think this day was probably the hardest, certainly in the top 3. And we'll sort of see why. So here's our essential problem. It's a graph problem. We're in these tunnels, and we have our starting space, double A, and each different valve. The valves are the nodes in the graph, and each one has tunnels leading to other valves. And we want to release. We want to turn the valves and release a certain amount of pressure, because the more pressure we release, I don't know, the volcano doesn't collapse on us or something. I don't know. So we have 30 seconds or 30 minutes. 30 is basically our time unit, and we want to close or open. I think we want to open as many valves as we can, or at least not just as many valves, but we want to open the valves that will release the maximum amount of cumulative pressure. And we can see only some of the valves actually have any flow. Some have zero flow, so there's no point in opening them. They're just sort of empty nodes in our graph. But it also costs a minute of time in order to open a valve, so that's kind of an important thing. So we can be in valve double A, and there are tunnels leading to DD, II, and BB. And so it takes 1 minute, I think, to travel down each of these tunnels, and then it takes 1 minute to open the valve. And we want to release as much pressure as we can. Now, like I said, this is a graph problem, and so my instinct was to do this using Dijkstra's algorithm. We can formulate this as a Dijkstra's algorithm problem in the following way. So recall, if you've watched any of my videos on Dijkstra's algorithm before, the way we use this, so we have this Dijkstra M. In fact, I'm just going to bring up the documentation on algorithm.search, because it's just going to be a lot easier if you see this. So Dijkstra M. How do we actually use Dijkstra's algorithm using this library? We have a few functions we have to pass in. So we have a function that takes one graph state and returns a list of, a foldable, but really just a list of other graph states that, the neighboring states that we can go to. We need a cost function, so how much does it cost us to go from one state to another? We need our end condition, when are we finished with this graph? And then we have our initial state. Those are the 4 elements that we need in order to call this function, in order to actually have a Dijkstra solution. Okay, how do we define these functions? So first we need our graph state. First we need to parse the input. Skip that step. But it's pretty straightforward. All these lines look essentially the same. We have a valve, we have some letters representing the valve, and has flow rate. We parse the flow rate, and we lead to the other valves. The key here is when we're parsing the other valves, this is a variable number of other valves, but I think it's always at least 1, so we can use set by 1. Very helpful combinator here. Otherwise, everything is pretty much just strings. Although there's a little trick where we have to, it's grammatically correct. So if we have one tunnel, we have this string. If we have multiple tunnels, it's this string. So parsing it is fairly straightforward, and what we're constructing basically is a hash map from strings to ints, so from each valve to the amount of pressure that is released by that valve, and also from each valve to the its neighbors. So we have an adjacency list, and we have the pressure list. So what's our graph state? And the graph state tells us, okay, what's the valve we are currently at? What is the current flow rate, and what's the current released rate? So the released rate starts at 0, and each time you open a valve, the amount of pressure, it's pressure per minute. So when we release a valve that has a flow of 22, we are releasing 22 units of pressure each minute that goes along. So doing the higher valued valves earlier on is better, because they count more for every additional minute. But we want to keep track of the total flowing rate, so the amount of pressure we haven't released, because that's going to be our cost. And that's going to be how we find the optimal solution. So we need the set of the valves that are still flowing, and we also need the current step, the current time frame we're at. That's how we're going to know when we're done. And we want the total amount of pressure that has been released. And let's now get into some of these functions. So how do we know when we're done? We're done once we hit our time limit. So for part 1, it's going to be 30 minutes. For part 2, it's going to end up being like 24 minutes, I think. So it has to be parameterized by this, but I don't even need flowing here, I don't think. But we just need this x. This x is the time portion of this constructor, and if x is greater than or equal to time limit, we're done. So that part's pretty easy. The cost function is also pretty easy. We want to look at the old time step and the new step, and we want to look at the flow rate. How much was flowing, how much pressure had not been released at that time step. And so we get the time difference and multiply the flow rate by that time difference. Okay, so that's our cost. Now, where the key logic is getting the neighbors. So we have ultimately these are constant parameters effectively. So we pass both of our inputs. We pass the pressure map, so the mapping from each node to its pressure, and we also pass a so basically what I pre-compute the distance from each valve to each valve, because what I was doing at the start was I was saying, oh, I'll just always step forward by 1 unit of time, and I'll just go to all of the different all the different neighboring nodes, even the ones that have 0 pressure. That turned out to be too slow. So what I did actually at the start, there's a ton of code dedicated to it at the bottom. I'm sure there's a simpler way to write for Floyd Warshall. So what I'm doing with this code is I'm pre-computing the graph distance from each valve to each valve, because I just want that to happen as quickly as possible when we get to the algorithm itself, when we get to this single actor search. And we'll see in part 2 that actually it's very important to have that pre-computed. And so, where are we? Okay, get neighbors. Okay, so we have this distance map. We can take any 2 nodes and find the distance between them pretty quickly. So how do we find the neighbors? Well, let's look at all of the you want to look at all of the nodes that are still flowing. So this flowing value, this is the set of nodes that we have not released yet. And we want to try to make a move using all of those different nodes. Okay, so that's what this tunnel move function is all about. I think previously I had a move where it was like, okay, either stand still or release a valve. Everything just turned out to be a tunnel move because we just assumed that we're going to release the valve. So what's the total distance we travel? Well, we get the distance from the current node to this new node. So remember, we're looping through this function for each of the different nodes that is still flowing. And we add 1 because the 1 is the minute we have to take in order to actually open the valve. So the new time step is going to be this current time step, and we're going to add our total distance. Now, what's the flow at the node? Well, we look up in our flow values. That's just a constant parameter. We get that from our input, and then we just have to calculate the new graph state. And there are 2 different cases. It's possible that the new step is beyond the time limit, that it takes us too long to actually reach that node to turn it off. And if that is the case, then what we do is we set the time, the final time, to the time limit, and we say the amount of pressure released is the time limit minus just the time limit minus the current step times the current release rate. I guess I sort of this is technically inaccurate, but it doesn't matter because so maybe if I explain the second case, it'll make sense why this is wrong. But the second case is, okay, we actually reach this new node, and we say, okay, well, the flowing rate, now we subtract the flow at that node. For the release rate, we add flow from that node. And for the total pressure that has been released, we take previous released value, and then we add the distance times the release rate. So the current release rate, that much is being released for all of the different steps that we take until we open this valve. But then we get a new release rate, and that's happening. That's why we update this parameter. And then we delete the node from our flowing set, and we set the new time step. So these are the two possible cases for what our next state is. Obviously, in this case, we don't actually reach the node to turn it off, but it doesn't matter. So if it turns out that there are no tunnel moves, if we've turned off, or if we have opened all the valves, all we need to do is just skip to the end, skip to our time limit, and we return one final graph state that is at the time limit where we've released a certain amount of pressure. So the time difference times the release rate, add that to the previous release value. And that's going to be our final graph state. So if we have any available tunnel moves, we will return those. Otherwise, we'll do this final case. So putting that together, we can do this single actor search. So we call Dijkstra n with all of our different inputs, passing a bunch of parameters. If we get nothing, I return like the we take max bound divide by 2. I forget what we're. This is just to signal if the answer is wrong and then we found nothing. But otherwise, we take the total pressure released and just call a bunch of functions because we need second to get the actual path, and then we need the last to get the final graph state, and then we want the total pressure released, which is part of that graph state. So this will basically get us our solution for part 1. We just do a single actor search with a time limit of 30. Now, what happens in part 2? In part 2, we train an elephant to do it with us, except so we have to take our first 4 minutes to train the elephant, but then the elephant can also turn off valves for us. So now we're doing a double actor search, except it gets really, really complicated if you try and break it down the exact same way. So the trick I found, and I didn't think of this trick myself, I perused the Reddit threads on this because I was getting really, really stuck. And it's still not a great trick for it doesn't make my code all that good. But I did get an answer in the end, and it was correct. But the basic trick here is that we have 2 different actors, and we're going to make a two disjoint sets of valves. Each actor will target one of those sets of valves and try to, that's going to be its target set. And we're going to loop through every possible series of disjoint sets. So you might say that's a lot, and you would be right. We can exclude half of the possible. So actually, I take set.power set. So all of the different combinations of nodes that are either in that or not. And so I think, let's see. So we assign one group of nodes as the player nodes, and we assign, we take the difference, and that's the nodes that the elephant will turn off. And then we say, okay, number of player, number of elephants, and we exclude all of them where we exclude all of the values where the number of player nodes is less than the number of elephant nodes, because it doesn't matter which is which, so this lets us cut off like half of the different options. And so then we do a single actor search with each of the 2 players, or with the player and with the elephant. We set the time limit as 26, and basically each of them will release a certain amount of pressure, and then we can add those values together. So I keep track, I do a loop where I process one element from this power set. And I wanted to keep track of the iteration numbers just so I could see my progress as this was running. But then each of them also, each time we will keep track of the max. It's either the previous max or we add these 2 together and we get a new maximum. So theoretically, this is very parallelizable in theory. So if I wrote my code in a somewhat better way and I, combined everything, this could be a very parallelizable solution. It turns out with the number of nodes we have, or I should say the number of, because we have 51 nodes in our graph, but most of them have a rate of 0. So if we have rate equals 0, so we can exclude 36 nodes, so it's only like 17. One of which is at the start. Actually, I'm not sure that's right, but it turns out that there are about 16,000 different elements in this power set. That's a lot. It took my solution about 30 minutes to run, but I did get an answer. So it was a long and painful process, but we take our single actor search from part 1, and we just run it twice, and we run that over all of the different elements of the power set, and you will get an answer. There are probably better ways to solve this, almost certainly. But that's how I got my solution. So go ahead and try this, and I'll be back with more with more videos in the next days and weeks. Hopefully my solutions will be better than this.